everybody. Today I want to look at, I guess, the main mechanisms we're given in Rust and Golang for some form of polymorphism and just being able to use various different types in different ways. We're going to be looking at traits versus basically Go's interfaces and kind of see how they compare. To do this, I have written two very similar packages, one in Rust and Go, and they are really just basic constructs for the sake of testing these details. So in the Rust side here, I have a struct A and a struct B. They are slightly different. One contains two U8s and one contains one I32. I also have a trait here called add1, and this is a method for adding one to each trait. And I've implemented this trait for both A and B types. So, these are the new methods. It's just easier in Rust if you've got those to just throw a thing together. I don't really feel like they get in the way of the code or feel too interrupty, but they're things you sometimes need in Go and sometimes can get away without. Same in Rust. And here I've implemented the add1 method for A, which does self.n plus 1 plus equals 1, and here I've implemented it for B. So the method for doing this is impl add1, the trait for B, and so we have to be specific that we are implementing this trait. Whereas in Go, I've done exactly the same. I've got a struct with an int32. Oh, these were supposed to be int8s, but it really doesn't make any difference. Seems to. Shouldn't actually change anything. And here I've defined the add1er method. I had to call it add1er to make it look like an interface because add1 is a public method, therefore it will need to be uppercase. So this is an add1er method interface, and these guys implement it. And in Go, it's of course possible to implement an interface without even realizing it, just by writing the appropriate methods. And that's not possible at all in Rust, as you can see, because we had to specifically say we are implementing the add1 trait. I have found a few advantages and disadvantages to that, so I'll come to some of those in a minute. So in Go, the code here is relatively short. That's just one page, and it's not much longer in Rust, especially if you take away the impl A and impl B on new. They all take one extra line of code basically to do the same thing. And then we've got the derive, debug, and partial equality, which are things we didn't need in Go, but because they're kind of assumed, but Rust relies on traits for almost everything, so they kind of needed deriving. And so our first test here, let mut v equal, and we make a new vec, a list of A's with 1, 2, and 3, and this vector is of type A, right? I've not actually specified anywhere, but I could put here, and this is a vec of A. If I don't do this, then it's just going to fill it in and make a guess anyway, because all of the content is A. So that's why I haven't bothered there. Now, if I wanted to add a B to this vector, I can't do that. But I can run through the list and call the add1 method on every element in this list, and I can assert that I have got a 2, a 3, and a 4, having added 1 to each of these numbers. This works the same for B, and I've added 1 to each, so I've had to assert that it's a 2, 3, a 3, 4, and a 4, 5. And there was an interesting detail in working with this in Go. So in our test side of things, I have a test for A where I've made this slice of A, and we've taken a pointer to A's as our content, and we know that this is a slice of pointer to A, so every pointer points to an A type, and we can call the add1 method, and this works. This is exactly the same for type B. So for B, I decided to test it with not using pointers, but in principle this would be the same for A, and there was a difference. In order to make this add1 work, we could in order to make the add one method work, we needed to put the result back into the vector, or the slice as it is in Go. I've called it vec just to make it clear we're talking about the same thing here. The test was slightly trickier to write in Go because you can't do a direct comparison on two slices in Go, so I didn't get to make a new slice. So yeah, I just had to do a comparison method direct and just run through the slice. And this is standard Go code, you know, you just run through a loop all the time and just do your thing. Often Go recommends that you do it this way. And here is the thing that you can't really do in the Rust mechanism. If we go for test, and I've called this test interface. Now I've got my my slice, I've called it vec for silly reasons really, but it's a slice of add one, and I can put an A in it, and then I can put a B in it, and then I can put another A in it, and I can run through the list and call add one on all of these. And of course, to implement the interface, they all had to be pointers because the interface was a pointer interface. It had to, because it changed them. And so it was easy to run through this list and add one. The challenge was actually getting the data back out and comparing it, because when I actually ran this, and it was very difficult to come up with a mechanism for comparing the interfaces, knowing the results, say I want to compare this with a type A and say is it the same. The only way I could do that was for each individual element to specifically assert its type here. So I ignored the OK because I knew it would be OK. So I had to do a direct assert this to a pointer to A, and then dereference that pointer to compare it to the ideal result, and if that was incorrect it would fail the test. This on the other hand actually continuously fails because, so it was difficult to do a comparison of an object against your type once you've put them into, once you've treated them as an interface. But it's easy to run the methods on it. And this is possible in Go because, of course, in Go everything is stored as a kind of a tuple, particularly for interfaces. So the first bit being the type of the pointer, and the second being the pointer. That way you know for certain what you can handle and that it will fit the mechanism. Another challenge we've got here is that actually a slice of type add one cannot be sent to a method that takes a slice of type interface empty interface, which is Rust Go's main mechanism for handling any type, is the empty interface. That means if you try and send this to a method that takes a slice of empty interface, you actually have to convert this slice beforehand to that kind of slice, and that means you've got a different result altogether, and so you'd have to convert it back somehow with assertions here and there. So that's a lot of work to send this to a method that takes a slice of empty interface. Whereas when you know for certain what type you have, someone can make a method that takes a vector, and it's not even very difficult to make a method in Rust that would be, we'll call it onVec, and this can take, and we just give that a type T, and this would take v colon vec of type T, and this will do something with that. Let's return and let's return a T. It doesn't really make much difference here. Maybe we would have to require that T has got clone or something, some method that T needs to have for us to be able to use it. And if len, this function would be tricky to write if its len is 0, so maybe we need to make it a result on T. But again, it's not beyond possible to throw together something that can handle this and any of our vectors, as long as the thing implemented clone, could be sent to this vector. Let's make that debug. Oh, if this implements debug, then we can just return a string. Res equals v dot iter. Now we're taking that. Let's take a pointer to a vector, and we can map this to, and we take our t, and then we just put format t. So now we've just formatted the result of the iteration, and we will join that and collect. This isn't even important. I don't really know why I'm focusing on this so much. We have an iterator on string. Can you just collect that into a string? Yeah, I think we probably can. Just collect. Actually, we can probably get rid of this altogether. And let's see if that compiles. Oh, obviously this needs a colon question mark, because we use debug, not display, right? If it has a debug trait, you can access it with this kind of method. Yeah, I left a load of downcasting stuff happening in the errors set here. So this compiles, and we can actually even fairly simply throw together a collection of these types, right? So I can then call the onVec method onVec of v, and v, and we should have a string result. So let's just well, I guess we can make a statement about what that should look like. Assert equals this should roughly say something like A2, A3, A. I don't know exactly what it will say, but when we run the test, it will tell us what it says, and we'll see if it runs out. Here we go, A2, A3, A4. This is what the debug actually does. So AN:2, AN:3. But the point was, it's very easy to write a method that takes a vector which contains any kind and works with it, or a limited subset of kinds and works with it, and that can be decided by the type. Even more powerfully, you can actually implement a trait for a vector of a specific subset of vectors based on their contents. And that's really handy for what you can do. The trait system is incredibly powerful, really weird, And you certainly gain a lot of simplicity in the Go version. But I could not write a function in Go that would take any kind of vector, any kind of slice, as long as it implemented this thing. I could only take a vector of a slice of something that implements this thing. Now, the primary reason that this is possible is, of course, that this actually is repeated, that this function exists for every caller that calls it with a different type. This function is actually compiled several times, and actually, as you see the compiler running, you get that impression as you see the same error show 4 times for the same line of code. And that's because the same function is being created 4 times. So if you know for certain what type you're using and you're using all of that type, Rust is a lot easier to use. If you don't know for certain what type you're going to be putting in, if you want a lot of polymorphism, I have found that Go is significantly easier to use on the interface side. However, this effect is basically achievable in Rust, and I've written a test for doing this, and we've used the standard box.box and a box of a trait object, and that's basically a pointer to with a reference to its kind. Now this box of type add1, so we now have a vector of box of type add1. And this box type is basically a pointer to with a reference to make sure its kind is also kind of stored. I think it mostly just stores its function table so that it can be operated on through that. And so by creating a vector of this box of trait objects, then whenever I add, I use a box new, which is a new box obviously, and then I put a new A object inside, and then another new box to put the B object inside. And this works because a box is a fixed size in memory and it stores a reference to the appropriate object. And it's not unpleasant to use as long as you are just using methods on that trait. But if you want to try and check against the type, then you're going to have a lot harder of a time. When I tried to write the assert equal method on this, it was a lot harder. I couldn't just create another vector of add1s and compare the two as I did down here. In order to compare them, I needed to be able to access the partial equality method, which I've derived for the top 2 classes, which is a very clever macros thing that Rust does. But the problem was I couldn't include that as part of this trait or a requirement for this trait, because if I do that, it will not compile. And the complaint is the add1 type cannot be made into an object. And the problem here is that the partial equality method requires an object of type self to be sent to it, but the compiler can't know at runtime if something is of type self, the same type as that object. And that is a trait of partial equality. And once you've boxed it, you really can't do that. So it says, no, we can't have a box of add1 type. So because partial equality requires that an object uses itself or another undefined type to be able to create its comparison, if we look here, the RHS, that can actually be itself, or you can define it inside, but it defaults to being self type, the capital S, and that causes that problem, that it doesn't know what that capital S is going to be from outside the box and can't make those tests work. And so it's not object safe, and so you can't use it. Cool. But we can. So now we actually have a mechanism using that function that we've created for testing that the add 1 has happened, at least. And that would be assert equal on V, and we'll compare it to, and this will probably be box A let's just use that assert and we'll see. It will fail, but at least we can get the right answer. Oh right, the function that we called it onVec, didn't we? OnVec of V. And it's got to be a reference so that we get it back. Quite happy to drop that box altogether, so we can just get rid of that, all of that, because it's just calling the debug method on the other thing. And then it was a B space x colon 3 space close brace, and get rid of that quote. Really close. I think we're just missing one space there. So overall, I find that there is more freedom in polymorphism on this side. In Go, you can actually use generated code, but I guess you can use generated code to do a lot in Rust. So there's more freedom for polymorphism on the Rust side overall. A little bit more typing because you have to write the box everywhere, but that's not unmanageable. But it's harder to get things out of a box than you might expect. The assertion that you can do in Go, which enables you to pull an item out by just asserting it to a type, because Go makes a point of storing that type information everywhere, isn't available in Rust, even when it's been boxed. So you can write, there is a workaround. You can turn it to a type any and pull it back out through this any type, a box of type any, and downcast it to the type you want, get a result. But that's quite a lot of work and a lot of awkward, but it is doable. It's a lot easier to achieve these kind of things with the generics that you get from Rust. Especially as you can type any object generically, whereas in Go, basically the only generic types are Rust. The only generic types are the slice and the hash map, or map as it's called. Everything else is fixed type, or you're using interfaces, and then reflection to make sure you've got the right type, which is a workable solution. Like using this pointer to a reference of A, you can always pull these things out. And there's a whole library on reflection which enables you to make some kinds of comparisons within things. But I think primarily because of the power of their generics in the trait system, I'm going to be sticking with Rust for a while. I like the type safety, I like the way it works these things through. It's possible I'll get more annoyed. I mean, I find the docs a lot easier to read with Go, but this is about the generics versus the interfaces, and I find the generic system easier to get what I want done. I hope you found that helpful. My name is Matt from Storyfeet.com, and I'll see you next week with a video that's probably not even closely related to this. Ta-ra.